Hi, this is Sean Gupta. In this video, we will talk about exponential and logarithmic modeling. Specifically, we will be interested in how we can use exponentials and logarithms to solve exercises and what kinds of exercises we might encounter. Specifically, why is it actually useful for the real world? I found it insightful to have a look at an example of bacteria growth that illustrates exponential growth. Have a look at this video. This video shows a bacteria colony. Initially it's very small, but as it represents exponential growth, it will grow very fast. Every 20 minutes, the number of bacteria essentially doubles. Now this is different from, let's say, linear growth, where for each minute you get a constant new number of bacteria. For example, each minute you get one new bacterium. Here, it doubles. The number doubles every 20 minutes. Okay, so how do you write down exponential growth in maths? Now, linear growth, use a linear equation, y equals mx plus b, where m and b are just any two numbers. Polynomial growth, use an equation such as this one, where you have powers of x squared, or x cubed. Exponential growth can be written as follows. There are many different ways of writing it down. This is just one way. A equals a0 times e to the power of kt. What does this mean? Well, a is the current value at a certain point in time. a0 is the initial value that you start with at time equals 0. E is a very special number. E means the x is the exponential number. It's a constant. And this constant is roughly equal to 2.72. T is the time taken, and k is a constant number that describes, for example, if something is growing, if it's positive it's growing, or if it's decaying, if it's negative it's decaying. So basically, if I tell you a0 and k, and I also tell you what t is, so for example t might be 5 years or 3 minutes, you can calculate how much something has grown from its initial value a0 to the current value a. You can also use logarithms. In this context, they're closely related, and as we will see later, they're often used to measure how intensive earthquakes are or how acidic chemical solutions are. Okay, let's look at this graphically. Here we have three graphs. Let's start with 50x. 50x is this red line here. It's a linear equation. Let's compare this with x cubed. X cubed is this blue graph here, and it's a cubic equation or cubic function. You can see it grows a lot faster. So the linear line will continue like this, with the cubic line shoots up here. But now compare this with the green line, 2 to the power of x. This is an exponential, and it grows really rapidly, much faster, of course, than the red line, but also a lot faster than the cubic line. And this illustrates that exponential growth is much stronger than polynomial growth. Okay, let's look at quite a different graph. This is the graph 10 times 0.5 to the power of x. And this represents exponential decay. Remember, exponentials don't have to always show growth, they can also show decay. And exponential decay basically means that things go to zero or decrease very fast. Exponential growth means they grow very fast, exponential decay means they become smaller very fast. Okay, let's have a look at an exercise that shows us how exponentials can be used to describe growth or decay and how we can calculate with them. In the town of illness, the number of cases of a particular disease D can be modeled by the equation D equals D0 times e to the power of kt, where t is the time in years. Using available medication, the number of cases is being reduced by 20% each year. There are 10,000 people with the disease today. Okay, so what do we know? 10,000 people have a disease today. The number of people with the disease decreases each year. How much does it decrease by? By 20%. How many people will have the disease after 1 year? Well, after 1 year means 20% less, so it's 80% of the number of people we started with. We started with 10,000 people, so that makes it 8,000 people. So after 1 year, 8,000 people will have the disease. Find the value of k correct to 3 decimal places. All right. So let's go back to the exercise. We have basically two unknown numbers, two constants, d0 and k. Remember, d0 represents the number of people who initially had the disease at time t equals 0. T equals 0 always remembers the start, or the start of time in maths. And k, which tells us about the decay rate, in this case, of the number of people with the disease. So we know at time equals 0, 10,000 people have it. And at time equals 1, 8,000 people have it. So we can basically substitute in these values twice. Let's start with the first one. T equals 0. We replace t with 0 here. And what is d? 10,000. Now k times 0 is 0. E to the power of 0 is 1. 1 just falls away. So d0 is 10,000. 10,000 people is the number of people who initially have the disease, which makes sense. Okay, so only k is missing. Let's substitute in the second data point. T equals 1, t equals 8,000. And k times 1 is 1. And we can divide by 10,000 both sides. 8,000 divided by 10,000 is 0.8. Let's take the logarithm to base e. And now if we have the logarithm and the exponential, they will cancel each other out. So log base e of e to the power of k becomes just k. And logarithm of 0.8 you can calculate with your calculator. So what do we get? K is minus 0.223. All right. Write the equation substituting in those values. We have d as 10,000 times e to the minus 0.223t. All right, not too bad. What does this mean? Well, 10,000 people start having the disease as time goes on. So if we plug in t equals 1 or t equals 2 or t equals 10, essentially e to the minus this expression will be less than 1. So overall d will be less than 10,000. This is why we have exponential decay. Find how long it will take for the number of people with the disease to be halved. Give your answer correct to the nearest year. Well, what's half of the people? That's 5,000 people. Let's plug it in. 5,000 equals 10,000 times e to the minus 0.223t. Divide by 10,000 on both sides. Take the logarithm. And again, logarithm and e to the power of cancel each other out. We get this. Now divide by minus 0.223, and t is roughly 3 years. Okay, remember, you can calculate this with your calculator. First do the logarithm, then divide. And we asked to give the answer correct to the nearest year. So we round this to 3 years. Next one, how long would it take for the number of people with the disease to be reduced to 100? Give your answer correct to the nearest year. This is essentially the same exercise as before, just with a different number. So on the left-hand side, we plug in 100 before we had 5,000. Again, divide by 10,000, take the logarithm base e. Logarithm base e and e to the power of cancel each other out. And divide by this number here, and we get around 21 years. It's 20.6, so we round up. Okay. Let's go to quite a different example. This is our second and last example for today. A number of earthquakes have been recorded in the Kalahari Desert. The earthquake's Richter magnitude, m, can be modeled by the equation m equals a times log base 10 e plus b, where e is the energy in joule. All right, so E, energy in joule, M, magnitude, how strong is the earthquake. You can see if E increases, the right-hand side will increase, and so the magnitude will increase. If there's more energy, the earthquake is stronger, which makes sense. Okay, if the Richter magnitude of an earthquake is 8.5 with an energy of 10 to the power of 17 joule, substitute the values into the equation. Okay, So magnitude is 8.5, that goes into the left hand side, and energy is 10 to the power of 17, we plug it in here for E. Now we have log base 10 of 10 to the power of something, those cancel each other out, and we're just left with 17, 8 times 17 or 17a. So overall 8.5 equals 17a plus b. Next, if the Richter magnitude of an earthquake is 3.8 with an energy of 10 to the power of 10 joule, substitute in the values. This is essentially the same as before. So left hand side 3.8, then we plug in 4e, 10 to the power of 10. Once again, log base 10 and 10 to the power of something cancel each other out. We get 10, so we have 10a plus b. Alright, why is this useful? Well, using these equations we can find the values of a and b. Okay, these are equations. How can we find a and b? Well, one way is we do first equation minus second equation. This way we will have b minus b, so b will go away. We'll just be left with an a that we can solve for. Alright, 8.5 minus 3.8 is 4.7, 17a minus 10a is 7a, and b minus b falls away, and we get an a of 0.671. Let's plug this value into either of those equations. In both cases we will get the value of b. Might as well take the second one, and b is 3.8 minus 10 times the value of a, and minus 2.91. Notice I'm plugging in the exact value here rather than the rounded value in order to avoid a rounding error. Okay, substitute those values back in. Okay, what do we get? This expression here. M is 0.67 log of e base 10 minus 2.91. Alright, so if I tell you the energy, you can calculate the magnitude. If I tell you the magnitude, you can also calculate the energy. So if we know the magnitude, find the energy. Okay, let's plug in 7.8. How do we solve for E? Well, let's first get rid of 2.91. We do plus 2.91 on both sides. Now in the second line. Divide by 0.67, so we leave the logarithm alone for now. And now, how to get rid of log base 10? We do 10 to the power of. This will cancel the logarithm out. So 10 to the power of this is this. Now we have e as 10 to the power of 16. Notice once again, I'm using the exact value because I only want to calculate everything at the end to avoid rounding error. So for this magnitude, 7.8, we get an energy of 10 to the power of 16 joule. If the energy is 10 to the power of 12 joule, find the magnitude. Okay, how's this different? Well, before we had the magnitude, had to find the energy. Now we have the energy, need to find the magnitude. Okay, in a way this is actually easier because we plug in 10 to the power of 12 for E. And how do we calculate things? Well, log base 10 of 10 to the power of 12 is 12. Once again, log base 10 and 10 to the power of cancel each other out. Okay, so 0.67 times 12 minus 2.91 gives us 5.13. Alright, so if the energy is 10 to the power of 12 joule, the magnitude is 5.13 on the Richter scale. Now, it's interesting to compare our answer from here with the answer from before. A magnitude of 5 on the Richter scale corresponds to an energy of 10 to the power of 12 joule. Before we had a magnitude of 8 corresponds to 10 to the power of 16 joule. 10 to the power of 16 is 10,000 times as much as 10 to the power of 12, but the magnitude is only 8, whereas before there was 5. So although these earthquakes are of very different intensity, in a way we can still measure them on the same scale. That's the power of the logarithm here. And that's the idea of the Richter scale. Okay, last slide, let's summarize things. What do we use exponentials and logarithms for? Well, we can use them to describe phenomena in nature that are nonlinear, and then we can also not model using quadratic equations or cubic equations or something like that. We can describe both growth and decay with them. This is the general formula for exponential growth or decay. A0 is your initial value, t is the time, and k is the rate constant. K is positive for growth and negative for decay. Alright, that's it for today. Thank you for watching.